Mm-hmm.
So welcome everybody to the discussion session for Monday. We had today 3 talks about microstructure and distinguishing microstructure from the black hole, and whether microstructure can give you anything different from the black hole result, or whether whatever averaging is going to give exactly what the black hole what the black hole gives. We had some, so we are 4 on the panel: Jeff Pennington, Daniel Meyerson, and Massimo Bianchi. I don't know how to do the presentations. In the past we did them based on the first name and then on the last name. So maybe it's best to do them based on the first name, like that. I think Daniel would be first, and then Jeff would be second, I'll be third, and Massimo will be fourth. Maybe that's a good. We have 5 minutes. The presentations are supposed to just throw in the air subjects for debate and for arguing and for gouging our eyes out. So if you are controversial, if you want to make crazy statements, feel free. If at the end you want something erased from the YouTube, I can do it. I've done it before. So if you say something and then you say I want this erased, I don't want this to be there on YouTube. Don't worry. We'll do it afterwards. So maybe we can begin with Daniel.
Okay. I mean, it's fine with me unless anybody else wants to go first. All right. So let me share. Okay, good. So all right. So like I was talking about this morning, right? This morning I introduced these little guys who I quite like, and so. Right. So let's talk a little bit. The idea of does this even make sense? This kind of came up a little bit in the talks, right? So does this even make sense to talk about going out and observing fuzzballs, or even or more generally, microstructure, or are we sort of doomed to always just look at objects as if they are black holes, right? If an object for all intents and purposes, for all observations that you can make, is going to behave and look like a black hole, then the distinction becomes almost a philosophical one, right? Let's see. Okay, good. So just sort of sort of the key point of my talk. This is not necessarily a plug for my talk, but I just want to kind of make a distinction here. The fuzzball phenomenology is an idea where you use fuzzballs as a model, right? A toy model for quantum gravity motivated top-down objects that you can study, as opposed to bottom-up objects that are typically studied in gravitational phenomenology, right? And so the microstate geometries within that, within fuzzballs, are explicit solutions that we can study. And what we hope to obtain from this, at most, let's say, is qualitative generic insights as to what such objects, such objects might give, right? So what such microstructure might give us. Okay, so this is sort of the idea, right? This is sort of very loose, I would say, from the idea of can we even distinguish in principle a fuzzball from a black hole, right? If we and we say we don't really expect to see a black hole, we expect to see some individual microstate, then you need to ask yourself the difficult question, is this something that we can actually hope to see, right? So in particular, let me say that there are certain. Okay, so first of all, let me say, just in case people are not aware, that typically one thinks of a black hole as a thermal average, a thermal ensemble over individual microstates, over fuzzballs. And so, okay, so this is because a black hole has a certain entropy, and so the entropy is associated to a certain number of states. And so there are certain statistical mechanical expectations that you have based on this kind of thermodynamic picture. And one of these very basic statistical mechanics expectations that you might have is that a typical state in the ensemble, right, in the quantum ensemble of fuzzballs, of microstates of the black hole, a typical state is going to be very, very similar to the average, to the thermodynamic average, which is the black hole, right? And what I mean by this kind of weird equation here is that for any observable, if you calculate its expectation value, because anything that you go out and measure, anything that would be a typical state, will have multipoles, love numbers, anything that we were talking about that is so close, exponentially close to the black hole result, that they are basically indistinguishable from the black hole, right? And so in this case, there would be no hope in detecting any kind of microstructure like this. Okay, so this is sort of the, I want to put this out there also to be aware of the objection, right? So there's 2 points that I want to make regarding this idea, these critique, let's say. The first thing is that we need to be very careful about what we want to do, what we want to be doing, right? So there's 2 different questions that we can be answering. And the first question is, can we distinguish an individual fuzzball from a different fuzzball, right? Can we distinguish different microstates from each other? But this is a different question than the question that I think we all have in mind, really, implicitly or explicitly, which is, can we distinguish the fact that there is a black hole from the fact that there is not a black hole, right? The fact that there is some microstate in the place of the black hole. And I think it's sort of obviously this second question that we're interested in when we talk about observations of fuzzballs, at least until we've gone out and observed that there is actually something out there that's not a black hole. This is the question that we're interested in. And I think this is a very important point to make because, while you might be worried about this first question, I think the second question has a lot more reason to expect their success, because anything that's generic for all microstates, but not necessary for the black hole, is something that you might be able to go out and measure. Okay, and I'll give you an example in a second. And I think also, although also this is something that came up already, right? Echoes might be exactly this kind of thing, right? They might be the echoes that we might see might not distinguish between different fuzzballs, but they might be able to distinguish between black hole and fuzzball, right? They might be able to distinguish between in this sense. And then the second point I want to make is that this idea of this sort of typical idea of typical statistical mechanics reasoning that tells you that what you go out and measure has to be in a typical state. This is maybe a little bit trickier, right? This is maybe a little bit more controversial, what I'm saying now, right? This is maybe a little trickier for the following reasons, right? We don't really know what the dynamics are of fuzzballs. And in particular, we don't really know what the dynamics are of a collapsing shell of matter when it reaches horizon scale, right? We talked about this already in different talks today. There might be some quantum tunneling going on at this horizon scale, which makes the dynamics very, very different than our classical intuition. Okay, and so the things that we need for the statistical mechanical intuition is things like ergodicity and thermal equilibrium, relaxing to some typical state, having started out in some atypical state, right? And so I think it's maybe a good question to ask. Is the dynamics of such black hole formation or microstate formation, is this something that's ergodic in the full quantum theory, right? Or to posit the other possibility, can we end up in some kind of a metastable, non-atypical state, right? Which is more of like a glassy state, right? Glass is not a typical state. Glass is not a ground state. It's a very long-lived metastable atypical state, and something like that might happen in black hole dynamics, black hole formation. That's something that Anthony Charles and I tried to model a little bit in a toy model a few years back. So that's just something that I want to throw out there. And I wanted to just give you an idea or an example of something where this might appear or be very important. So again, this is the idea where at horizon scales, you might have this quantum tunneling effects that become very, very large, very, very important due to the large phase space that opens up to your matter once it collapses down to horizon scales. And so, this is, of course, a very difficult thing to study because you need to be studying formation, evolution, dynamics in general. But what you might reason, and this is something that Thomas Hertog and Hartl did a few years back, is that these quantum transitions in the formation process could lead to something like a gravitational wave burst at exactly this point where the quantum tunneling effects become large, right? So this might be exactly in this merger phase, which is unfortunately so difficult to model and to study because you need numerical relativity if you're looking at two merging black holes. But this might also be a place to look for a smoking gun for these kind of quantum tunneling, quantum transition effects that would appear in this kind of idea. Okay, so that's sort of those are sort of the wild ideas that I wanted to put out there, to first of all put out the critique about what you might have against what you might say regarding typical states, and then also try to understand how we might get away from this critique. Okay. I see that Nayash has his hand up. I don't know if Yosef, you want to do questions now or wait until
do questions
everybody.
now at the end. I don't know. I mean, it's up to
you.
Maybe you can put one question now, and then we can put more.
I think it's better just to have everybody sort of say things first and then really dive in.
Okay, then we'll do that.
All right.
Okay.
All right. Okay.
Okay. I think Jeff is your turn.
Okay, let me share screen on my iPad. Okay.
Yep.
Okay, cool. So I think I'm sort of on this panel as a representative of people who don't spend terribly much of their lives thinking about puzzles and so on. So, as such, I just wanted to make some very basic and hopefully uncontroversial comments about what we know to be true just about random states and so on. So I'm going to assume, for the purposes of this 5 minutes, obviously it's an assumption that people may complain about later, that sort of the thermal ensemble, which we can define in precise sense in ADS-CFT and flat space, we maybe think there's something well defined anyway, but we don't know how to define it as well, should be dual to just an ordinary classical black hole and not some distinct like fuzzball geometry or something like that. And I just want to make some comments about how such an assumption would constrain the observables of individual black hole microstates, whatever they might be. And basically, I'm just going to make comments assuming that a black hole is just some large number, little n qubits. But I think you can make all the comments I'm making precise for CFT eigenstates as well. So yeah, here are just some facts. If we have black hole as n qubits and the equivalent of thermal ensemble, i.e. the maximally mixed state, it's just 2 to the minus n times the identity as a classical black hole, then what's true about a random state in that Hilbert space, a random black hole microstate? Well, the first comment is that for any sort of nice, simple observable, O, maybe a product of observables on each qubit, then we should have the expectation value of O and our random typical microstate psi is just given by the thermal expectation value, plus some correction that will generically be exponentially suppressed with respect to n. So that's comment 1. Comment 2 is that if we allow ourselves to consider more complicated operators, then we can obviously find operators where the expectation value of psi is very different from the thermal ensemble. For example, an operator where psi is an eigenstate. But generically, those operators will be exponentially complicated. So if we want to do some unitary circuit, then maybe measure 1 qubit or a few qubits, and then undo the unitary circuit, then that unitary circuit will need to be exponentially long with respect to n. And the third fact is that these statements 1 and 2 are true for randomly chosen states with incredibly high probability. It's actually a probability that's doubly exponentially close to 1. Okay, so that's a comment. Of course, a random state in the Hilbert space is presumably not described by some individual microstate. It's presumably an exponential superposition over eigenstates. So the individual eigenstates themselves can definitely be not look random, can look very different. So if I have some preferred basis psi I of states in this Hilbert space, for example, the basis of fuzzballs or whatever it might be, then I can certainly have the sort of I have the expectation value of, say, a Pauli operator. Some simple observable for all states in that Hilbert space can be for all states in that basis can be very different from the thermal expectation value. the obvious example is just if these are the computational basis products of zeros and ones, then the expectations of Z operators are very different to thermal expectations. I should say one thing that can't be true about these psi-Is is they can't be the energy eigenstates in our CFT or whatever, because the eigenstate thermalization hypothesis says that those eigenstates should look thermal. You know, it's a hypothesis, but it's a pretty well-established one at this point for a very generic quantum system. And the other thing is, of course, that even if you have some basis where all these expectation values are very different, then they should still average to the thermal expectation value. That's just some very basic maths of you know, everything being linear, and so you can put stuff inside the expectation value and get a trace of the maximally mixed state times it. So I guess the only other comment to make is you know, does this mean that if we assume this assumption about the thermal ensemble looking classical, can there ever be a universal signature of individual microstates as opposed to the thermal ensemble or as opposed to random states? And there can. It's debatable how whether it's observable, but there's sort of two things that can universally differ in specific states in a basis from random states. And one option is that it just needs to be some nonlinear function of the state, right? The reason we could do this trick with actual observables is because they're linear. So an obvious example of this is entanglement entropy. If the n qubits get split into two sets of n over 2 qubits, then, for example, for any state in the computational basis, we have no entanglement entropy between the two sets of n over 2 qubits. But for either the thermal ensemble or indeed for the typical microstate, then you have the entanglement entropy is n over 2. So this is, of course, not an observable, it's nonlinear. But there's things that are still nonlinear. Sorry, the definition of the computational basis being asked in the chat, I just mean states of the form 0, 1, 0, 0, so on the n qubits. Products of zeros and ones. But that's just an example. It could be any basis of product states in this case. Option 2 is it can be a linear observable, but just an observable that acts on multiple copies of the same microstate. So again, you know, to actually have this observable in the real universe, you'd need to somehow know that you had multiple black holes in the same microstate. Not really practical, but just as a mathematical test, an obvious example closely related to this entanglement entropy is what's called a swap operator. That basically, you know, you have two copies of your microstate, and it just swaps, let's say the first, again, n over 2 qubits, system 1, and swaps them with system 2. And in that case, the expectation value for a particular microstate is going to be equal to 1, just because you preserve the state by swapping the two things. This is assuming, again, that these are computational basis states. But for a random typical state in the Hilbert space, then you get 2 to the minus n over 2, order 2 to the minus n over 2. So yeah, that's all the comments I have to make. Hopefully, as mathematical statements, they're pretty uncontroversial and just true. Their relevance to black holes and microstructure and so on may be more controversial.
Thanks. I think it's my turn now with M. I have a Romanian name which comes after M, so but I guess okay, so the whole desktop. So I just had a few comments which are similar to what the previous two speakers have said. Again, the question is, you know, can we distinguish microstructure from the black hole? If you look, so, you know, let's suppose we're in an ideal world, and, you know, we have constructed e to the s horizontal microstate geometries, which form a basis for the Hilbert space. We poured the champagne. We are very happy. We solved all the problems of the planet. The question is then, what do we do with the classical black hole solution? And there's one question, which is indeed, as Jeff and Daniel were mentioning, that the black hole may give you the thermodynamic average of the microstates. The black hole solution can give you the thermodynamic average. And in particular, it can give the correct physics of the typical black hole microstates at the horizon scale. Daniel, in a sense, argued for something a bit different. He was arguing that there is a thermodynamic average, but it doesn't need to be the black hole geometry. It could be something. It could be some other beast. The second possibility is that the black hole, the one with the solution with the horizon and so on and so forth, is an unphysical solution which has too much symmetry, which needs to be thrown away because it doesn't give the correct averages. This is the second possibility. Again, if you build it into the horizontal microstates, those are the only two options. And possibility number two, before you say, you shouldn't throw away the black hole is holy, we should realize that in string theory, that we have many examples when a very symmetric configuration is thrown away in favor of a less symmetric configuration which displays the correct physics, in particular in Polchinski-Strassler, Klebanov-Strassler, the D-105 system, giant gravitons, just to name a few. So we have examples in string theory where a very symmetrical spherical solution is thrown away and it's not dual in particular to any state of the dual CFT, not even to a thermodynamic average. Now, what's the evidence for possibility number one? One can make an argument similar to what Jeff was making. Let's suppose you have some Hilbert space. There are e to the s microstate geometries, and I can parameterize them with a vector with a Hilbert space with a wave function psi I, and I can look at some quantum superposition of them. And I have the typical one, which will be some parameter times the first one, some other parameter times the second one, and so on and so forth. The whole thing beautifully normalized. And I can take, for example, I can take this this microstate geometries, and I can compute in each and every one of them the multiple moments. Multiple moments Daniel we saw in Daniel's talk and also in Paulo's talk. You can describe multiple moments. You can compute the gravitational multiples of all these guys. They're all finite. However, if you look at the typical state, which is going to be some superposition of these beasts, in the typical state, they're going to average to 0. And in a typical state, all these moments, which correspond in the dual D5 CFT to VEVs, are going to be over the e to the minus s over 2, actually. But okay, over the e to the minus s. So they're going to be exponentially suppressed. Now, there's a question actually whether this line of reasoning. So I understand very well this line of reasoning from an ADS-CFT perspective. It makes perfect sense. However, if I think about the sun, for example, the sun has gazillions of microstates. Yet, if I look at the multiples of the microstates of the sun, they are not exponentially suppressed. If I just, if I just take all the atoms in the sun, the multiples of these configurations are not going to be exponentially suppressed. They can be they can be suppressed as a power of the entropy, but not as an exponential of the entropy. So one question which I want to throw is that, how correct is this line of reasoning? Are we assuming some decoherence? Are we assuming that maybe because the sun is big and shining and, we are seeing it all the time, somehow, it decoheres and we see individual microstates, while for the black hole, we're just assuming the quantum superposition, we're assuming some Schrodinger cat kind of superposition. This is one question which I want to throw in the discussion. There's another possibility though. Okay, maybe the microstates don't differ from the black hole result by some exponentially small stuff, but maybe they're still distributed in somewhere around the black hole values. And for example, multiple moments, we argued in a recent paper that they do, even if the group in Roma, for example, argued that they don't. So, there's some discussion there. That's a discussion for those of you who love possible complementarity, that, maybe this is also saying that possibility one is correct. An infalling observer basically falling through, doesn't see any difference from the black hole except, some tiny effects. That's possibility number one. For possibility number two, one thing which is happening is that some quantities, they're always different from the black hole. One of them is the mass gap. For example, if you look at the extremal black hole, the extremal black hole has an infinite throat. And if you look at microstate geometries, all of them, and also if you look at the dual D105 CFT, all of them have a mass gap, which comes again from having a long throat with the cap. You solve the wave equation in the cap, you find the gap. It's a very clean calculation, and it comes exactly to be the one from the CFT. And the mass gap is always positive, unlike the black hole mass gap, which is 0. You can also compute autocs, and Massimo is going to talk more about that, I think. You can also compute love numbers, for example, in microstate geometries versus the black hole. Maybe not, entirely kosher gravitational love numbers, but more other perturbations. And for example, for the black hole, low numbers are 0, but you can argue that for some microstates, they are going to be non-zero, and they all have the same sign. So essentially, what it's going to mean is that if you look at some operator and you look at expectation value in these typical states, you will not get the black result, the black hole result. One can also discuss, so today there's a big discussion about dissipation, reflectivity, new degrees of freedom, echoes, non-extremal multiples. One can make many arguments and so a lot of things. But the first three things are things which one can make a rather straightforward calculation using the known extremal and supersymmetric fastballs. And there you can see that one, at first glance, it looks like if I'm averaging over them, I'm not going to get the black hole result. However, there's a caveat. And basically, the caveat is that in the black hole result, you say, the black hole near horizon has an ADS2, and there's no gap, and so on and so forth. However, if you treat low energy physics around the ADS2 vacuum correctly, then there'll be a talk by Joachim Turiac tomorrow. One can argue that even from this ADS2, you can actually see a mass gap, even from the black hole solution, even from the extremal black hole. So one can argue that if you treat it correctly, you'll see a mass gap there in the black hole, and what microstate geometries are finding matches the black hole. So maybe this is not such a strong argument as it looks. And the last piece of information I'm trying to throw in the game is that if you look in the ADS2 CFT1 setups, there you can show that the CFT1 has many conformal symmetry breaking BPS ground states. So there are many solutions which are asymptotically ADS2, which have a cap in the infrared. They're obtained by taking some nice limits of superstrata or bubbling solutions, and moreover, they are dual to some states of the CFT, which by construction break conformal invariance. There's also a solution in the game, which is the Poincaré ADS2 vacuum, which I'm just showing here as an infinite throat. The microstate geometries have a finite throat, and the question is, I have all these gravity solutions, the ones which have a cap, and the one which doesn't have a cap, and the question is, does there exist a BPS ground state of the CFT 0+1, which is conformally invariant, and which would be holographically dual to the uncapped ADS2. And the answer for the system, as we argued in the paper with Pierre Hyman and David Turton, and also we have some preliminary work with Miguel Paulos, the answer is no. And this again seems to be supporting possibility number 2. Essentially, what you can argue using just basic CFT1 is that the empty Poincaré ADS2 is not going to be dual to any of the ground states of the CFT, similar to the Poincaré ADS3 actually. So in a sense, this again is supporting the possibility that the black hole result, whatever it is not dual to anybody in the CFT. The CFT cannot have a conformal invariant ground state, and therefore all the microstates, if they average to something which doesn't look like the black hole result. And that's again something which comes, which is comparable to what Daniel has been saying. That's it.
Should I take over?
Yes, let me stop the share.
Oh, sorry.
Yeah, we can see it. Command L, I think. I think it's going to be Command L.
Sorry.
Or Control L. I think.
Sorry. Okay. So, okay. I will repeat some of the statements that were already made. I mean, even if individual microstates may behave differently from the ensemble, one, at least in the standard law, expects that superimposing a statistically significant fraction would get, for any classical measure, the results that are expected for a black hole. So one should not be able to discriminate black holes from fastball. and only quantum measurements can expose correlations that allow for distinguishing the two objects. Clearly, this is hampered by two problems. First of all, we don't know most of the microstates for large BPS black holes, let alone for more realistic non-BPS black holes like Kerr and Newman black holes. And also, this is something that I'm not sure it's been stressed significantly, but depending on the probe or the observer, different superpositions may be relevant. And this comes within this stringy description that probably Josip was alluding to at the end. My claim is that, which is in line with what Daniel was suggesting, that certain fastball observable may not average to the corresponding black hole values. This is also in line with what Josip was suggesting. Clearly, multipolar structure, quasi-normal modes, tidal response, gravitational memory, and these are sort of classical effects, and then also some semi-classical or quantum effects like Hawking radiation, superradiance, and angular regions instability can expose these different behaviors. Okay, now this is clearly very similar to what Daniel has been saying earlier on and later today. But anyway, we know that for general Kerr-Newman black hole in 4 dimension, all the characteristics like mass, spin, and multiple moments are completely determined by 2 parameters, the mass and this parameter A, which is the ratio of the angular momentum to the mass. And in particular, due to axial symmetry and equatorial symmetry, the multiple moments, the mass multiple moments with even index are proportional to the mass 2 times A to the 2L, and the current multiple moments are proportional to A to the 2L plus 1, while the odd mass multiple moments and the even current multiple moments are equal to 0. The similar situation takes place for STU black holes, and the regular BPS limit requires the parameter A to go into 0. Clearly, by definition, we expect that the mass of whichever fastball we consider must be the same as the black hole mass, or the spin should average to the spin of the black hole, which is 0, for instance, for BPS black hole in 4 dimensions, and the charge also. Yet for higher multiple moments, there might be deviation, which can be exposed by taking ratios. Now, let me stress this. I mean, clearly, that might be difficult to measure higher multiple moments from gravitational wave detection. But here we are probably dealing with a question of principle, not a detailed experimental issue, which might be solved in 200 years from now. Now, also, the equatorial symmetry, which is characteristic of a Kerr black hole, can be broken by generic microstates, and then the presence of odd mass multiples or even current multiples may expose the structure of a microstructure instead of a black hole. We performed, as was already mentioned, a kind of a very naive statistical analysis of a class of BPS microstate geometries by studying the effect of moving a parameter, which was measuring the distance between the 3 centers. And we noticed that in the 90% of the cases, the multiple moments of the fastball were larger than the multiple moments of the Kerr black hole. This was eventually disproven by Josip and collaborators in the non-BPS microstate case. But once again, this deviation from the expected behavior of multiple moments for Kerr black hole can be a smoking gun for a microstructure at the horizon. Also, quasi-normal modes are another topic that has been explored both by Paolo and Daniel earlier on today. And the only thing I would like to say in connection with the comment by Joseph is that this parameter lambda, which essentially in the WKB approximation gives rise to the imaginary part of the quasi-normal mode frequency, is related to the Lyapunov exponent. And we also observed that typically the Lyapunov exponent for fastball is smaller than the Lyapunov exponent for a black hole with the same mass. In particular, we also noticed that the bound on chaos that is set by the temperature can be violated near extremality. And very recently, based on work by Grassi and collaborators, we also devised some approach to computing quasi-normal modes of black holes, DP branes, and fastballs, in particular for circular fastballs that are microstates of two-charge system, which do not correspond to bona fide large black holes in 5 dimensions. Then was also mentioned that the tidal response coefficient may differ quite significantly from the standard Kerr black hole case, because in the Kerr black hole case, the static tidal response coefficient, which is real, called the lab numbers, vanish identically, and the imaginary part can be non-zero because of the frame Dargin, but is given by some specific expression. And this can be compared to fastball cases by using various methods and approximations. Now, another topic that has not been covered so far is the issue of gravitational memory. This is related to the fact that scattering amplitudes in gravity expose 1/omega pole in the soft limit. And by going to the time domain, this by Fourier transform, this tells us that there is a shift in the metric perturbation from early retarded time, you go into minus infinity, to late retarded time, which is completely universal. It's proportional to the Newton constant divided by R, and it's proportional to this combination of the momenta of the particle involved in the scattering process. Now, clearly, we cannot compute reliably any fastball mergers, but in a heterotic string, we can study sort of objects which are two-charge states, which mimic small black holes, but they can be very massive. And we can study the merger of two such BPS objects to a non-BPS one, and with the production of gravitational wave. And in string theory, these simple pole that appear in the pure gravitational case comes with a series of pole on the real axis at tree level, which are shifted from the real axis by quantum effects, that give rise to a series in which is an exponential in the retarded time parameter, and it's also non-perturbative in alpha prime, so it cannot be seen in any low energy approximation of string theory. And the signal is not, if you want, a simple displacement of a detector that is due to the passage of gravitational wave, but it gets modulated by this phase. And if one notice that the TPL...
Massimo, at some point, we shouldn't be... Panelists shouldn't go on too long. We need to
sure.
Pretty soon. So if you can finish up in the next minute, that would be great.
Okay. So by some numerology, by taking omega to be 50 hertz, and one over alpha prime to be gut scale, and the masses involved in these two black holes to be something like 30 solar masses, one can get a detectable signal for near future advanced LIGO and BIRD. Now, there are also these semi-classical observable that can discriminate black holes from horizonless geometry. Clearly, there cannot be any thermal radiation from for unitary evolution, and also super radiance that has been used recently to set Swampwan-like bounds on axion dark matter should be reconsidered in the case of a microstructure. Clearly, the way to test whether one can really have different behavior for microstructure from black holes is to go back to simple models like two or three charge system that emit a single holographic description and test the possibility of distinguishing microstructure from black holes. Probably also, I didn't mention this model by Joseph that was mentioned at the end, and these can really expose the fact that black hole averages are not the observable that we may find looking carefully in the sky. Thanks.
Thanks. So I guess we can open this to the discussion. I think Nayesh had a question before, and then Paolo. Question, comment. Maybe it's the best people raise the hand, or I mean, I don't know. What's the best?
There are two raise hands.
So I should just apologize because I have a lecture just in 3 minutes. So I have to leave, but maybe you guys can talk about it afterwards. So I don't know of any example where deviations from thermal state is suppressed exponentially. So you may think about unrealistic observables, but no realistic observable is exponentially suppressed. They're all, they're suppressed by power law. For example, the example is viscous corrections to thermal distributions. So I more precisely, when you are out of equilibrium, which realistic situations we have power laws, not exponential. So that was my comment, that I don't know of any example where you have actually in real world you have exponential suppression. It's always a power law.
Sounds good.
I think this is related to what I was trying to say about the fact that you use this typical state argument is related to we assume that everything has relaxed to some typical to a typical state, right? Which happens in ergodic processes, but you don't necessarily know that this is true. At least that's how I'm interpreting the comment.
Paolo, I think you're next.
Yeah, thanks. So I have a couple of questions, but let me start with one. So it's related with this average procedure and whether the average matches the black hole value or not. So something that worries me a bit is that in order to make this average, one needs, well, the sort of weighting function, but let us suppose that all states weigh the same, but then one needs all the states allowed for the theory. And it seems to me that in many cases, we don't have a full description of all microstates. So isn't this always an issue then to compute the average? Because, for example, one can compute the average for a given quantity, love number or whatever, quasi-normal modes, but it will always be average over a subset of all solutions. So whatever conclusion that one can draw will be limited by that. Is this correct or not?
My feeling is that by definition, at least for the extremal black hole, by definition, everything different from the horizon will not have an infinite throat. If you have an infinite throat, you have a horizon. So if you don't have an infinite throat and you solve the wave equation, essentially the mass gap, for example, will be finite. So whatever one builds, even if it's not a microstate geometry, even if at this point, by some accident, maybe we are still 5 years away from understanding what the typical microstates are, just because in the extremal case, the black hole has an infinite throat and microstate should have a finite throat, by construction, you are guaranteed that if you solve the wave equation, you'll get a mass gap. So there, for example, I think the argument one can make it pretty generically that all the microstate geometries will have a finite mass gap, while the black hole has a zero mass gap. But then the arguments against this, there are some arguments that in the black hole, if you treat the black hole correctly, using all the quantum things into account, you'll get a finite mass gap. I think Jeffrey, at some point, we discussed during one of his talks, and we discussed about whether in a classical solution with the classical horizon, you can still get a finite mass gap. And I remember Jeffrey had some arguments that.
Yeah, I mean, it's really Joachim and Luca's arguments, but one thing I should say is that the argument is that if you have a BPS black hole, then you can do the gravity path integral and find mass gap, because you end up the dimensional reduction is what's called super JT gravity, and this has a mass gap. If you have a non-BPS but near extremal black hole, then their arguments are that you don't have a mass gap, that you just have you have large corrections to the entropy, like the density of states tends to 0 as you approach extremality, but there's no mass gap and there's no degeneracy of the ground state because you don't have BPS protection.
That's interesting, actually, because some of the microstate, I mean, in a sense, we can build non-BPS microstate geometries. We can build them for the NEC, for the Neo Horizon Extremal Current, for the almost BPS black hole. But there, the problem is if you go to the Neo Horizon, you still get some sort of ADS2 region. So I don't know what they mean by non. I mean, if by non-extremal, I mean, if there's an ADS2 region, then I think you can always argue that, at least from our perspective, there should be a mass gap.
I think that Paolo was asking a different question. He was asking the question, is there any toy model where we have some control over all the microstates? The answer is that for two-charge system and maybe for some three-charge system, we have this control. So probably this can be used as toy models for asking and answering to you. This was my last point.
Yeah, I guess my question was more going beyond the toy model. I mean, just to rephrase, Josip was mentioning about the average of the love number being always, say, bigger than 0, and therefore, the love number being, say, positive or anyway with like definite sign, and therefore the average is either positive or negative. And therefore it does not average the black hole value. But my question there would be, are you considering all possible states when you do the average? Is this something you...
No, of course, no. We're just doing some specialized subset. I mean, they are very hard to compute for.
But yeah, this is precisely my question. But then how, I mean, at this stage, is the average even meaningful in the sense that one can never exclude the possibility that there is another subset that will give you, say, negative log numbers, and when you average the two subsets, you give again 0, right?
I think that, I mean, the log numbers, if you put the black hole in ADS-CFT, so if you do flat space, you can discuss log numbers, but if you put it in ADS-3, then the calculation is the same as the Green's function one. So it's basically the too light, too heavy Green function. And there, I think the argument is also that there'll be some reflectivity. There'll be something you deform the microstate, and something comes out, and that's basically and I think it has to do with the fact that the wave equation is solved. I mean, if you just throw a wave down this throat, it will go to the bottom. Okay, maybe there will be strings excited and so on and so forth, but something will come out, and I think that's basically. I think the argument is generic.
But no, I mean, I agree. I totally believe that the log numbers will be non-zero. What it's harder to me to understand is whether they should have a definite sign for all possible microstates.
I think, Daniel, I mean, we discussed it. We made some toy calculation.
Yes, but this was in. I mean, it was in 5 dimensions, and it was for superstrata, a particular case of superstrata. I mean, I would be maybe more careful in saying that. I think, I mean, because like Paolo says, if you don't have at least even a nice basis, right, like you do have for D1, D5, it's very hard to make these definitive statements, I think, because you don't know if like maybe there's a sector that you're not describing that there's something going on in the, like maybe it's not captured by a supergravity solution, or maybe there's some funky feature in it where your intuition is sort of flipped on its head or something like that. I mean, that's maybe too conservative of me, but what I'd like to talk about the two-charge system though, because that's been raised as a toy example where we do know all of the microstates, right? But this was also raised by Joseph as as an example of this proposal 2, if I can call it that, right, where we really need to get rid of the average geometry, or we need to get rid of the black hole geometry. And that black hole geometry doesn't exist, and we really need to replace it by the D1, D5 microstates, right? I think we understand that. But I think that's sort of missing the observable angle point, right? Because for all intents and purposes, the black hole geometry, or the singular geometry for the D1, D5, is a very good approximation to what is the average state, right? So even though technically speaking, we need to throw this away as a well-behaved solution because it's singular and because it doesn't actually correspond to the average state, you know, it still corresponds very well to the average of the ensemble of D1, D5 states. And so, and this was, I think, the point of you know, this paper from a while ago by Raju and I forget the other author, but you know that the average D1, D5 state is so close to the black hole that you're never going to see a difference between a typical state and the black hole.
Were these quantitative? I mean, did they compute any explicit observable, like for instance, there are quasi-normal modes both of D1, D5 and D1, D5 fastball, and we can study the average of the fastballs one and compare them to the D1, D5 geometry. I mean, geometry. I mean, solution.
No, I think there's definitely room for studying the right observable in these kind of things, right? Yeah.
Can I jump in and ask a question?
All right. I think Stam had his hand up before me.
Yeah. Go ahead.
Let me lower my hand there. I'm wondering where the following analogy breaks down. If I were to consider electromagnetism, then I know that an electromagnetic wave is a classical configuration of electromagnetic fields. The quantum, and it's a superposition of photons. And if I can resolve individual photons, then I will measure photon shot noise, that if the number of photons is quote unquote small, has a Poisson distribution, and therefore I would see departures from typicality because the distribution isn't symmetric. Where of course, if I were to take configurations that have microscopic number of photons, I would get a typical electromagnetic field configuration that is perfectly well behaved. So I would have naively thought that if someone comes along and says, these are the black hole microstates, we found them from superstrata, BPS, I don't know, D1, D5, fine. If we can resolve the microstates, and then comes along Samir and says, no, I have an alternative, they are fuzzballs. Well, let's call these these are two different categories of the quantum degrees of freedom whose classical limit at some point is going to describe the black hole geometry. So I'm a bit confused by Josef's concern that there are departures from typicality if we're averaging small numbers, or if we're not averaging them properly, especially in disordered systems. And I was just wondering whether this analogy that I mentioned, can we pinpoint where it breaks down for black holes, microstates, fuzzballs, and so forth? Or is it a good guide to somewhere?
Hard to say. I need to think about this. I don't have a clear. I don't know if other panelists have a clear, more clear understanding. Personally, I mean, for me, indeed, you know, things could be averaging, but I think you know, one likely option is that, you know, they'll be averaging to something which is not the black hole. So, you know, maybe by some.
If I average a small number of photons, I'm not going to get an electromagnetic wave. Or if I average it quote unquote badly, if I average it with the correct factor, then I will get at some appropriate limit an electromagnetic wave if I have a lot of photons.
Yeah, this is actually, I mean, it has to do with how important quantum effects are, and I think you know, for most of these things, you know, again, I had this argument about the sun that, you know, if you average all the things in the sun, you know, you're not going to get a spherically symmetric configuration. So whatever, you know, you'll never get a spherically symmetric emitting thing. So if you average all the sun microstates, and in particular, the sun is not spherically symmetric. So whatever we are observing is not a spherically symmetric thing. So I think it may have to do. It may be a half answer in that direction.
The only comment I would make is just again, even just in the low energy gravitational path integral or whatever, you can see for near extremal black holes that you're getting large corrections to the classical saddle. You can see the quantum fluctuations about the classical saddle start to matter a lot. And so we can see that that's a case where we shouldn't expect the classical answer to be right without even knowing anything about fuzzballs or anything like that. So I'd be slightly worried about like learning too many lessons from doing some calculations involving extremal fuzzballs and then trying to learn something about Schwarzschild black holes from that, when for Schwarzschild black holes, in the gravitational path integral, the classical saddle seems very, very solid and doesn't have large fluctuations.
Would that be related? Would that be related to the idea that to see shot noise, you need to see individual Hawking quanta probably, and to see individual Hawking quanta, it's much easier to see it when the temperature is 0, basically.
Well, yes, but then it's trickier to resolve. But yeah, it should be.
Yeah, but I mean, a large black hole has a very low temperature, so it's even more controversial because we would expect more classical behavior for a large black hole rather than a small one.
But then I would argue that the deterministically chaotic behavior of the microstates would, in fact, give the dominant temperature, which would not be well defined precisely because the system is disordered.
Emil, did you want to jump in?
Oh, yeah. It was as long as this discussion has run its course. You wanted to bring up something a little bit different, which is that it seems like there's a big difference between any of these cap geometries or putting some kind of boundary condition near the horizon, which is that one predicts a spectrum of excitations which is gapped, not just the gap that Joseph was talking about, or which is a gap between the ground state and the first excited state, but there's a regular set of excitations above that, which have a quasi-particle spectrum. And so, take your favorite microstate geometry, solve the wave equation in it, you're going to have some regular set of normal mode excitations above some ground state. And that seems to me very much different from the level statistics that you get by studying black holes of any sort. It's this, maybe this is an observation which should be deferred to the chaos and scrambling panel, but might as well make it here that basically any kind of microstate geometry that you're going to construct will have an excitation spectrum which has Poisson statistics rather than random matrix statistics. And that seems to me very different from what you expect to look like, to behave like a black hole. And this would be related to fast scrambling and other things of that sort as well. So I think there's in that sort of, I don't know if there's anything observable about that, because we're talking about, the excitation spectrum about something which is, very, very far down in the cap and so very redshifted. But just as a matter of principle, it seems like there's a huge difference between any of these things that are being discussed and black holes.
I think actually there is no, I think the distinction is much smaller. So what you know in a black hole is that indeed there are two states at somewhere in the spectrum which have a difference of energy of order e to the minus s. But if you imagine having e to the s fuzzballs, which are all supersymmetric, on top of each of them you have a tower. So fuzzball number 1 is a tower, 1 over n-5, 2 over n-5, 3 over n-5, but it's actually not like that. The difference between the 0 and the first one has usually some value, and then the difference between 2, 3, 3, 4, 5, 4, 5, and so on and so forth have a different spacing. And for some reason, which you have no idea, which you don't understand, but which comes out from the calculation, between 0 and 1, there is one gap, and then between 1, 2, 2, 3, 3, 4, 5, 5, and so on and so forth, there's a different gap.
Doesn't matter. It's still a Fock space.
Indeed, but then the point is, if you think about the whole Hilbert space of the problem, you have all these supersymmetric ground states. On top of each of them, you have a tower. And in these towers, you have e to the s towers. Clearly, the gap between state number 15 in tower number 17 and state number something else in tower number something else will be of order e to the minus s, because you have e to the s towers.
It's not the sizes of the gaps. It's about whether you have a eigenstatistic repulsion or not. Whether the eigenvalues are getting repulsed from one another and therefore becoming roughly equally spaced. If you have e to the s independent towers, you'll have no correlation between
you have a large replication of Poisson statistics.
Exactly.
So you have a large.
It's totally different from
this. I need to understand that. Okay, I need to understand this because I mean maybe I don't understand the full thing.
So if I have a random Hamiltonian or something, then the spacing between eigenvalues, you'll very rarely have two eigenvalues very close together because eigenvalues want to repel. So it's like you have it's really a logarithm. It's like charged particles with like a logarithmic potential between them, the eigenvalue statistics. And so they'll end up being roughly in an approximate sort of lattice, like evenly spaced out. But if those eigenvalues are just coming from a very large number of independent towers that are not interacting with one another, then there's no reason why they won't just sometimes have two eigenvalues basically sitting on top of each other.
Yes, but I don't know. I don't see the problem with that because they can be in the very different sectors. I can have the gas in one corner of the room, and it will have some eigenvalues. I can have the gas in the other corner of the room. It can have another bunch of eigenvalues. Why would the eigenvalues in one corner and the eigenvalues in the other corner repel each other? Because in these microstates, for example, they live in different superselection sectors, at least in some bubbling examples. So I can have a solution which has 15 bubbles of some fluxes and some topology, and I have another solution of 17 bubbles. They cannot go from one to the other because going from one to the other just means you need a huge amount of tunneling to. So the microstates don't talk to each other. There's no reason why some guy in the tower in one of them cannot be arbitrarily close to some other guy in some other tower in a different tower.
Yeah, and that's a problem.
Okay, why is there a problem? Okay, is there some argument in the? So okay, let's take the
if you're saying they don't, if you're saying that the quantum correction, if you're saying these states don't strongly mix, right? If so, there's no fast scrambling. You can just write down this bubble solution and look at the quasi-particle spectrum around it. Then the spectrum is going to be well approximated by your solution. It's going to have Poisson statistics, and you will definitely not agree with what we believe to be true about black holes.
There is scrambling because of the tunneling. So clearly, as you showed with Andrea and with Daniel and with Bert, these microstates can tunnel into each other. So even if you think about it,
that gets back to what Jeff was saying earlier, that the quantum fluctuations are large, and then this classical picture is not a reliable guide to what's going on.
Because its tunneling is going to be so large. But the question is, okay.
Something has to turn Poisson statistics into random matrix statistics. And so if you're going to rely on some dodge that there's some large tunneling between these different microstate geometries, then you're saying there are large fluctuations and everything's out of control.
When you do have photon statistics, for a small number of photons, you do have Poisson statistics. When the number of photons becomes large, the Poisson statistics become Gaussian, go over to a Gaussian, and there's in a relatively quote-unquote smooth way. Of course, what is hidden behind that is that the photons aren't interacting unless. So that is I think something. Whereas here the microstates. So the question is whether the microstates, how are the microstates assumed to interact, so that in a way that affects their statistics. It's not just Poisson statistics. Because if it were just Poisson statistics, they will be photons. So there's something more, I guess.
Yeah, I guess I would just say that from a boundary point of view for a Schwarzschild black hole, not near extremality or anything, we can be really very confident that the statistics are random matrix statistics and not Gaussian statistics or something. So it does not look like a large number of free particles. It looks like
sorry, my computer just
interacting
died.
slowing couple of things.
I don't know if this is still streaming to.
We can still hear you, Joseph.
Sorry, my computer just died. I'm on a tablet.
We can hear.
Is the YouTube streaming still working?
Yeah,
Yep.
it seems so.
Ah, okay. Because I cannot see any. So
Sorry,
what was the answer? Sorry,
could you make a more precise statement about what does a random matrix statistic look like as opposed to simply a Gaussian? What happens to the strong law of large numbers? I mean,
it's the pair it's the pair statistics of the eigenvalues, not the individual It's not the eigenvalue distribution itself. It's the pair statistics. How likely is it that there are two nearby eigenvalues of the Hamiltonian?
That has a 0 at 0.
So the statistics themselves can have some whatever distribution you like. The question is, if I look at any pair and I look at the eigenvalues that are nearby to one another, is it likely or not that a pair of eigenvalues can be arbitrarily close? So in the case where you have random matrix statistics, the pair probability goes to 0 as the two eigenvalues coincide. Whereas, and that's just simply because of the sort of angular degree of freedom averaging of a random matrix. On the other hand, if you have just plunk down some random numbers and you ask, are there two random numbers that are arbitrarily close to each other? The answer is obviously yes, and that's Poisson statistics.
So would it be fair to say that there's the idea that individual microstates, as far as we understand, have this tower of spaced states, which is very different than the random matrix tower that you expect from in the average black hole. But then the idea is that you might get out of this, or you might be able to retrieve the black hole statistics again by using this large tunneling argument, right? And that might be that gives you the black hole statistics, and it also tells you that the classical picture is going to be sort of breaking down. But is it fair to say that since we don't really know how much the tunneling happens, how strong it is exactly, at least for this particular idea, that the tower of states might be somewhat different still, even with the tunneling, might be somewhat different than the random matrix black hole expectation, right? So that this is in some sense an observable still of difference between microstructure and black hole, right? Because we simply just don't know enough about the tunneling dynamics to make definitive statements like this, right?
But we know that the tunneling between BPS microstates is of order e to the minus s, so this we know for sure. So, I mean,
is that enough to?
Any two bubbling solutions have e to the minus s tunneling between them. I mean, that's not.
I mean, with some coefficient, and I mean, is that enough to say to conclude that is that it? I mean, is that all you need?
I think that's enough. I mean, my feeling is that for the long throats, I mean, that's what we had in our paper with Andrea and with Bert. I mean, essentially, if you are in the same superselection, so going from one bubbling solution to the other one just moves you from different superselection sectors, and between any two of them, the tunneling is over e to the minus s. So, and actually, the coefficient was bigger than 1, if I remember. It was not exponentially large, so it was, there was a big number a in front of this tunneling, and it was actually quite large. So
it was very model dependent also in how we calculate the tunneling amplitude and everything.
But shouldn't this coefficient in front also be of order exponential s precisely, because
no. So the point is, there's an e to the minus s tunneling, and then you have e to the s of available endpoints. Okay. So the point is, you have e to the minus s probability of tunneling, and you have e to the s available endpoints, and then the tunneling will take place with probability over the 1.
I mean, that was what I was mentioning, that in this case, what is special to the system is that there's an exponential s in addition that multiplies the exponential minus s of the tunneling.
So somehow, I mean, you are saying that because of this tunneling, somehow, the 15th microstate, the 15th eigenstates on top of one the 15th excitation on top of one guy and the 17th guy on top of the other guy should somehow repel each other. I mean, that's basically what you want because of this random matrix picture.
Well, something has to happen to completely rearrange the level statistics. And so I guess the concern would be that your starting point is some large ensemble of things that have Poisson level statistics. And then you're relying on some rapid tunneling to engineer some massive change in the 2-point function of the eigenvalue spectrum, which sounds to me like a calculation that's gone out of control.
I think there's a more mundane answer to this question. I'm going to talk a little bit about this on Thursday, but we have now examples of non-BPS superstrata, and the spectrum is a nonlinear function of the excitation amplitudes. So, just mundane nonlinearities in the non-BPS equations can actually shift the spectrum around.
But the shifting is not enough.
I don't think you have to appeal to. I don't think you have to appeal to any tunneling argument. There's just simply a classical mechanism by which you excite something over here and it changes the spectrum over there. And so, the transition to chaos, I think, is just going to be some simple fact that, what's deceptive about BPS is that everything inside is sort of linear, but the nonlinearities of non-BPS equations actually can just shift the spectrum around.
I think it's more radical than that.
It's
you see, it's the words one uses in something like the SYK model is that there are no quasi-particles, and like Subir Sachdev makes a big deal out of this in his way he describes things. Is that that there just are no recognizable quasi-particles in the excitation spectrum of the theory when you actually diagonalize the Hamiltonian of something as simple as SYK with 40 spins. So at best, I would say the microstate geometry might decay to something else, which has a rather different spectral properties. But it itself does not exhibit the spectral properties of a black hole.
Did you expect that any microstate geometry, any individual microstate geometry should exhibit the spectrum of a classical black hole? The microstate geometry is a quantum object.
Well, I mean, look, all of this structure is intimately tied with properties of the horizon. The fast scrambling, the lack of identifiable quasi-particle excitations, right? Because you just try to solve the wave equation when there actually is a horizon, everything falls through, right? You have these quasi-normal modes, everything decays. There are no resonances and no echoes and whatnot. So all this structure that's being found is precisely because there's no horizon. So the minute you have sort of enough structure that it starts mimicking a horizon, then the question for me is if you have to sort of stand on your head with microstate geometries to sort of mimic the properties we know the black hole has, do you then end up basically recreating something that's functionally equivalent to having a horizon?
We don't know the black hole has these properties. We know the thermal ensemble has these properties. The fact that the black hole classical solution with the horizon is due to the black hole to the thermal ensemble, that's, again, another question. There's no calculation in the bulk which shows this level spacing and so on. This is just ADS-CFT and,
there are calculations like OTOC, OTOX and stuff like that.
Sorry, I cannot hear. Can you speak a bit closer?
Sorry, there are calculations that are symptomatic of quantum chaos, that are symptomatic of having those sort of level spacings. Like you can't directly calculate the level spacings, but things like the ramp, the plateau, these are things that can be calculated in the bulk in simple models. and they look like you have chaotic level spaces, eigenvalue function.
Yes, no, but you can get chaotic again. I mean, I think the argument is, okay, if I just look at a bunch of microstate geometry of supersymmetric ground states, and I look at towers on top of them, they are going to look chaotic. I mean, they're just going to be like different. I mean, if I just look at all the possible towers and I just put them on top of each other, they will look very chaotic. I mean, I don't see. I think it's not the chaoticness, which is the chaoticity, or I don't know what the right word is, which is the problem. I think the problem is, the problem which Emil is pointing out is that the eigenvalues don't repel, and that's, I think, this is the more subtle issue.
I mean, maybe it's a feature of the spectrum near BPS, and that I'm not sure I would subscribe to this, but one might take the dodge that as you go near extremality, the scrambling gets very long, and so the transition to chaos may take a long enough that there's some long-lived excitations which might have some, quasi-particle-like structure. But the thing that makes me worry about that is that we have examples of systems where you are near extremality, like JT gravity, where all these properties seem to be features of the spectrum in the dynamics.
But the excitations are long-lived because the gap is small. I mean, because the gap between two different. I mean, why are the excitations long-lived? I mean.
Oh, I'm just pulling that out of thin air. I'm just saying, if you wanted to maintain some picture where some kind of cap geometry was a good approximation to the generic state of affairs, you would need to postulate that sort of the typical near extremal microstate has long-lived quasi-particle excitations. And that's somehow allowed because the scrambling is slow near extremality.
There are toy models where scrambling can be faster, but more precisely at extremality. So the limit from non-extremality to extremality, I'm not sure whether it might be as smooth as, or there might be conservation laws that there are toy models where you are at extremality and nevertheless you have fast scrambling.
Yeah, I agree with that. In fact, as I said before, I mean, this limit on chaos given by the temperature can be violated near extremality, and this is precisely what we found.
I think that two more questions. This was actually very interesting. Maybe we should keep on discussing in private. I think it's something which I didn't appreciate before, and I think it's an interesting.
Can I ask a question that goes in a different direction? Jeff made this remark in his presentation about doing measurements of exponentially long circuits, or the kinds of measurements where you could actually tell the difference between a microstate and an ensemble average. And I was wondering whether he could conjecture any such process that you might do on a black hole. What would I do if I gave you a black hole and you wanted to go and can you give us an example of something where there's a very long set of process measurements I could do that would tell?
I mean, I think the point is that the exponentially long circuit will depend on what the microstate is. Like, it's just a fact that if I have any state psi, then I can do a unitary circuit that will convert that into any other state, and therefore I can convert it into a state that has observables that are very non-thermal, right?
Yeah, right.
So it always the exponential time to do that is more a statement about how hard it is to do that rather than the fact that you can, because of course you can, because you always can if you have a pure state. So there are things, there's closely related things where you sort of can say what the circuit is to do that. These things called the PETS map and stuff like that. But normally they're sort of, basically what you do is you define them in a way that treats your particular state as like a black box. So it's like your definition of the circuit is defined in terms of the state. And then sometimes you can do a Euclidean quantum gravity path integral calculation that says that it works. but it's not really telling you what the circuit is, because it's like your circuit is defined in terms of like inner products of different microstates and stuff like that. I could with a bit of time I could construct some example like that. Like,
but isn't this requiring you to know what the state? Isn't this a chicken and egg problem? Suppose the black hole, you don't know the state, and therefore can you ever know what to do with it in order to see whether it's a microstate or an ensemble average?
Yeah, no, basically. So what I could do, for example, is if you could give me very explicitly two microstates, then you could construct a circuit that will make those two microstates distinguishable. But if you already know how those two microstates work and like how they're defined in your Hilbert space and stuff like that, right? Like, if you give me them in the CFT, then I could do it.
But is this then an answerable question based on what you just said? You're saying that in order to know how to turn this thing, to measure that this is a microstate, you actually have to know the microstate itself before you do the measurement.
No, I think what he's saying is, to answer Nick's question, correct me if I'm wrong, but you need to do exponentially many of these observations.
Okay. Right, good.
To distinguish if you, right, that's one way of saying, right, I don't know what the state is, I'm going to see if I'm going to see if it's this state by doing this observation. I'm going to see if it's this state.
I have to do a lot of experiments.
It's not a philosophically,
There's two things you could do. One is to okay, let's say I know it's one of two different microstates. Okay, one way to distinguish them is that they'll have exponentially small differences in like expectation values of simple observables. I do exponentially many different simple experiments, and I can work out the answer. If I am able to keep producing these states again. The other is I do a single very complicated experiment that distinguishes them. But how to do that complicated experiment, you need to know a lot more about like what those two microstates are. Like, there's sort of, for obvious reasons, without specifying, without more input from the physics of those microstates, you can't say anything about how you would actually do that experiment.
There's a question by Paolo, I think.
Yeah. I think he left, but he left questions. Yes.
Oh, he left the questions. Okay.
Well, I'm still here. I didn't want to interrupt the discussion. So
yes.
if you
no, but maybe we should. Go ahead. Can you ask them directly or?
Yeah, it was a bit long. So the question was related, Joseph, to your comment about throwing away the black hole. Because being the black hole part of the spectrum of the solution, I mean, somehow to me the interpretation would be easier if it was not there. So the question is, since there is a black hole or a family of black holes in the spectrum of the solution, I guess that they can sort of cook up some initial data for a collapse in order to form that particular black hole. So for example, I tune the initial energy and angular momentum of some dust, for example, and then make it collapse and form the black hole. So I guess is the statement that the one that this would be a very fine-tuned initial data and generically I should form instead regular microstates or not? And some related question is, when two neutron stars, for example, merge, they can form and collapse directly to a black hole in general relativity. In this theory, how should I interpret this? That they will form a regular microstate, but then where does the matter go somehow? Because when they collapse, I mean, the remnant is a black hole. So the question is probably about matter theory. What happens to them when they collapse?
So I have two examples from string theory, which are in a sense, similar to this. I mean, which can give some intuition. One of them is this Polchinski-Strassler story. When you have n equals 4 deformed to n equals 1, it's a field theory which is confining and has many vacua. And there, one can build a spherically symmetric vacuum, which is very similar to the black hole, because it has spherical symmetry and so on and so forth. And you can ask, okay, I have the real vacuum of the theory, which I know, which were counted ages ago by Donaghy and Witten, which are like the vacuum of the n equals 1 star theory, which correspond to the D3 brane polarizing and puffing up into some big fat large configurations of large scale. The black hole, in a sense, is like this. So the black hole is, from this perspective, the black hole is on the same footing as a singular solution. I would say that it's not dual to anybody. And at least in the ADS2 example, where we know the CFT, there's a CFT1, and the CFT1 again cannot have a conformal invariant ground state. So the black hole solution with the horizon and stuff should not even exist in the spectrum. At least in the ADS2 calculation, it doesn't, because there we have many capped solutions. They are dual to states which are supersymmetric and have a mass gap. But then if the CFT also has a state which is supersymmetric and doesn't have a mass gap, and it's translation invariant, then you can show with some CFT1 arguments that the CFT should be topological and should have no dynamics, and then you can actually, which you can rule out by explicit calculations. So there, I would say, at least in the ADS2 case, I would say that the black hole should be thrown away. It's not dual to anybody. You can never obtain it because it's not in the spectrum, which is the same as the Polchinski-Strasser solution. The Polchinski-Strasser solution, again, the spherically symmetric one is not in the spectrum, or in the giant graviton, or in the LLM. The LLM solution, which doesn't have bubbles, it's not in the spectrum. It doesn't belong to the theory. It's just some garbage artifact which comes from imposing a huge amount of spherical symmetry where none should exist. And it's just an artifact of your equations. You are throwing away physics. You are forcing a spherically symmetric ansatz, and then the system says, it's screaming and saying, no, I don't want to be spherically symmetric. That's in a sense.
Let me add, because there was a question. Paolo was also asking, what's the fate of meta? I mean, clearly only the relevant quantum numbers will be preserved in this transition. So if the meta that you were collapsing had a charge or something, that would be would remain in the microstate geometry, and if not, everything else would be lost. I mean.
But for example, the tunneling. I mean, we have done the tunneling for a bunch of M2 brains collapsing to form an M2 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 black hole, which is dual to the D1D5 black hole. So there we did the calculation with Andrea and Daniel and Bert Verknock. And there, for example, you can show that to go from a bunch of D brains which are just moving on the Coulomb branch very happily, you can tunnel from this bunch of D brains into these multiple bubbles. And then you can tunnel from the bubbles to other bubbles, and you can just tunnel from one to the other one. So once you have these two neutron stars, if they are merging and they are within the Schwarzschild radius, or close enough, then there will be a huge tunneling probability, and they'll just become a black hole by tunneling. But this is the only way. Otherwise, again, if you don't have this quantum tunneling, then if you collapse a shell of dust, for example, if you don't have quantum tunneling, the metric side of the shell of dust will be Schwarzschild. So then if your shell of dust is 15 megaparsecs long, it will collapse, and then it will form the Schwarzschild solution with an empty interior, and then it will keep on collapsing, and then 60 hours in the future it will form a singularity. And if you want to build something at the horizon, the information has to come back in time 60 hours to mess up your horizon. So that's very unlikely. So the only way you form fastballs, and the only way you prevent the horizon is by this tunneling. So somehow, this neutron stars should also be tunneling into this configuration.
So in particular, just to answer, because Paolo also asked, does this mean that we need to, if we want to have a black hole collapse, do we need to have very specific initial conditions? No, right? It's really that where you would typically say in your collapse or merger or whatever, you trust GR as long as the curvatures don't get too large. What we're saying with this tunneling picture is actually no, we even stop trusting the GR result, which gives you a black hole, even when the curvatures are not large, right? That's this quantum tunneling effect that becomes important at horizon scales, even without large curvatures, right? And so in that sense, there should be, in fact, no initial conditions that lead to the formation of a black hole, right? If this picture is correct, it's not even just a measure zero subset of the actual states. It's really just there's no states that are the exact black hole.
But then, sorry, this would be accounting for, say, a full quantum theory, right? I mean, if I just stick with I don't know, n equal to supergravity, then I guess maybe even the opposite is true, that I will always form a black hole.
Yes.
Likely.
Yes.
Okay.
I think if you take some initial matter configuration in n equals 2 supergravity, where both black holes and the microstates exist, then you won't be able to see this effect, right? Because it's a purely non-perturbative quantum effect, these tunneling effects, and so you will just collapse into a black hole. Yes, I think that's correct.
I guess my question is if the black hole, classical black hole solution is just meant to be some artifact that isn't real at all, then how do you explain the amount of success that there's been in understanding the thermal field double state on a CFT using a classical two-sided black hole. And just to sort of list off some of the things that's got us, I mean, obviously it has the correct entanglement entropy across the horizon, but also mutual information between subregions on the two sides, like correlation functions, including out-of-target ordered correlation functions, being consistent with bounds of chaos, but also consistent with the general features we should expect of a chaotic CFT. You have things like traversable wormholes, where you literally have something going through the wormhole from one side to the other, that was first discovered in the bulk by thinking about a classical black hole solution, but we now understand pretty well from the quantum information point of view why this effect should occur. There's a huge amount of stuff that the thermal field double state is both, treating it as a classical two-sided black hole has both like taught us and we've learned from, and seems
isn't that like saying, well, we've learned a lot from saddle point approximations and we can approximate lots of things with saddle point approximations, but that's not the whole truth. And it certainly doesn't tell you the details you need to know.
Sure, it's the dismissing it as an artifact that, like, if you want to say that it's telling you some approximation to the thing, but there's some deeper story that it looks different, then that's fine. But I think Joseph was just sort of saying, oh, that's an artifact that just isn't really in theory at all. Like,
I think that's, a saddle point approximation sometimes is in the theory and sometimes it isn't. But I think we all believe that the Schwarzschild solution and these other things are useful, very powerful tools. But they're Joseph saying there's thermodynamic average, and in some sense.
So to give you an example, in the D1D5 system, for example, there's a naive D1D5 solution, again, which is a singular solution. And, it's a very useful solution. You can compute all the averages, you can compute it, you can use it as a saddle point, you can do a lot of stuff with it. And, you can count its entropy, for example, before stormage of APA, Sen was able to count the entropy using the extended horizon. And then you can look at all these corrections, which the Bolkar has been looking at. You can do a huge amount of physics with a naive singular D1D5 black hole. But we know very well that in the D1D5 system, that singular black hole with the stretched horizon is not dual to anybody, even if you can get this, again, huge amount of beautiful physics out of it. So the question is, whether there's any pure state dual to it or not. And, there the answer is no in the D1D5. So from that perspective, I think this is one of the reasons which, again, why I believe this black hole solution, again, it's nice, you can get physics out of it, you can get a huge amount of physics of information, but it's not going to be dual to any pure state, at least based on the D1D5 intuition. And also in this
the thermal field double is a pure state, and it's correctly computing expectation values for that pure state, for correctly computing all sorts of complicated observables for that state. In what sense would it be not actually dual to that state? What does it mean to say that, oh, sure, it's computing a lot?
Thermal field double is not a pure state in one theory. The thermal field double is pure state with two boundaries with two different theories. So from that perspective, also global ADS2, you can say global ADS2, which has two boundaries, is a pure state in two different theories. No problem with that. The question is it a pure state in one theory? If I just look at the theory on the right, and that's I think the.
Okay. I don't think anyone would claim that it's a pure state in one theory, but maybe this is just me.
Yeah.
But I guess more broadly, I guess Jeff and Joseph are maybe not as far apart as they might appear. Joseph, you presented a kind of a dichotomy of, is this solution really useful and it computes lots of averages and it tells us lots of physics, or is it completely unphysical and has to be thrown away? And does it have to be strictly either or, black and white, or could it be that both statements are true in some sense that, as a matter of complete principle, the solution is singular, it doesn't correspond to any particular pure states of a single-sided CFT, and yet it's still incredibly useful and tells you lots of properties of averages and thermal states, thermal
I think ensembles. I agree with Jeff. I agree with Jeff that the thermal, if you look at ADS2, for example, the single-sided CFT, pure ADS2 is not a dual of that. Pure ADS2, which has two boundaries, is dual to a pure state of two CFTs. I have no problem with that. That's, I'm ecstatic about that. The problem is if I look at a single-sided CFT and I'm just saying I have a solution which is ADS2, which has an infinite throat, the question is, from a single-sided CFT perspective, is this dual to any CFT state? And there the answer is no. So I think the point is there's a huge amount, there are many, this is in a sense where the subtlety lays. Nobody says that ADS2 the infinite global, I mean, the ADS2 with two boundaries is not, I mean, that's a nice pure state, you know, this, which is the same as the thermal field double state in this limit. I don't have a problem with that. The problem is if you look at a single CFT, and which is, you know, what we need in the D1D5. And I think the same is in the D1D5. In D1D5, okay, global ADS3 is just, it's a nice solution. Nobody has a problem with that. It's Poincare ADS3 with a periodic boundary condition, which is problematic, which is singular.
But you can still get lots of valid physics out of this solution, which is in principle singular and should be discarded. I guess.
Indeed.
So it's not that if you have to completely discard the solution as a matter of principle because it's singular. It's not that you can't get any good physics out of it. It's not that you do every possible calculation you might do with it is wrong. No.
Still do. The calculations are correct. I totally agree with that. And you know, and even the argument that you know you can capture. I mean, in the D1D5 system, you can even show that you can capture average quantities of all the microstates. So you know, there, for example, you know, this argument that you know, if you look at this naive solution, but the point is the naive solution again, just pure ADS3, Poincare ADS3 with periodic D1D5 direction is not dual to any CFT state. That's in that sense is not dual. I mean, in that sense, that solution doesn't belong to the spectrum.
Mm-hmm. Yeah. But for certain physics, like Imo was saying, that the black hole's key property is that it's incredibly absorptive. And so for quantities that you might want to compute that depend strongly on that, the classical black hole solution, even if in principle it's not a valid solution, can still be an incredibly useful tool for computing lots of interesting quantities.
I have a question, both for Jeff and Joseph. It seems there is something a bit fast, right? Because you can also think about wormhole geometries, which have horizons and they're two-sided. And I think this is exactly the example, one of the examples that Jeff brings up. Those objects we're not supposed to throw away, right? But from the picture that Joseph is describing, that I shouldn't even have a process that can make such a thing. So I don't know. I'm a little confused, or maybe the argument is going a little too fast.
In a single CFT, you cannot make such a thing. I mean, if I have a single, you know, D1D5 CFT, I can do as much garbage as I want to it. I'll never be able to make the
No, that's true. But the statement is, you know, if you consider such a geometry, the question is, when you have a collapse of matter of anything, what does it form? The picture that you presented is the process of the collapse will always form something that does not have a horizon, right? And this statement, you know, isn't specific. What is the theory that I'm looking at? Is it the double CFT or the single CFT? So it's a question of what is happening locally and how I should think about this from the full, more complete theory. There seems to be something that is not quite consistent in this picture.
Yeah, so I don't know how to go from two CFTs to a single one. So, you know, you know, maybe that's you know, one of the biases of working too much with Poincare ADS and not, I mean, in the D1D5, for example, you know, if you just do Poincare, you know, there's a single copy, I mean, you don't have the double copy, and you don't, I mean, it's just a simple question. And there, I think the answer is clear that, you know, in that particular CFT, there's no, I mean, there you just have the cap solutions. You don't have anything. You don't have anything else. If you look at two CFTs, if you do, I mean, thermal field double, you know, there, you know, there's no problem. You know, I don't think that there anybody denies that the black hole solution, you know, is dual to pure state. It can compute stuff, but that's in two different CFTs. You know, two different.
Yeah, I guess my comment would be just like the two-sided black hole gets a lot of stuff right for the thermal field double state. The black hole formed from collapse, just classical solution, also gets a lot of stuff right without.
But I don't think that it gets. I mean, I don't think it gets anything which the microstates cannot get. But okay, maybe that's my.
I mean, we don't have the microstates for Schwarzschild black hole.
No, but you know, for example, you know, I mean, in terms of calculation, in terms of calculations, again, there's an entropy, but you know, that's a statistical, that's a thermodynamic quantity. So there are many things which are thermodynamic quantities. In a sense, to show it's a pure state, you need to get something which is pure statistics, which is not thermodynamics.
I mean, for a black hole formed from collapse, then if you want to know whether it's a pure state, you can just use the Ryutakinaga formula, and it has an entropy of 0. So I think under the normal rules of ADS-CFT, then that state where it's formed from collapse certainly has zero entropy.
But then why would it have a horizon, you know?
I mean, the normal rules of ADS-CFT, a horizon is not a von Neumann entropy. It's a thermodynamic entropy, but it's not a like microscopic entropy. The rule for a microscopic entropy is it's the Ryo-Takanagi formula, quantum extremal surface description. You can get as fancy or not fancy you want, but basically it says find the smallest area surface homologous to some boundary or boundary subregion. For a black hole formed from collapse, then it's a space-time with trivial homology. So the empty surface, just like the surface whose set of points is the empty set, that's homologous to the boundary, and it has a zero entropy, so it has zero area. So the normal rules would say that the collapse geometry has zero entropy.
But then that's exactly what we are saying. That we're saying that this is not a black hole with a classical horizon.
But I don't see why a horizon automatically means it has to have non-zero von Neumann entropy.
Yeah, maybe that's what at least I'm confused about that.
A horizon certainly has something to do with entropy, but I think the usual story that there's some great work by Netta Engelhardt now and Wall on this and so on, is that it's sort of a coarse-grained entropy. It's saying what's the highest entropy state that has the same expectation values for simple observables or something like that. It's not telling you about the actual microscopic entropy of that individual state.
But I think
that's given by the RT formula, and we can compute it for a black hole formed from collapse.
So I guess the only question is, okay, so if the entropy of the configuration is zero, then I guess the only question is, okay, what's the difference between that and the fastball? It's just that you have vacuum at the horizon versus something else.
Yeah, exactly.
Okay.
Yeah.
Okay. I didn't appreciate that. This. The black hole formed from collapse has zero entropy. That's.
Yeah, thanks. I think this is exactly what sort of addresses the question that I was having, right? Not every time you make a horizon, you should think of microstates that exist to a large number.
Okay, are there any more questions? I think we are 15 minutes over time. If the discussion keeps on, I don't know if people are tired or should discuss more, or we have, it's just Monday. We have
I think we
have 4 more days. I don't know.
I think
Nick, you are the.
Well, I was going to say we're about half hour over, but there's been a good discussion. So I think we should just preserve our stamina and save our energies for the next season. Finish at 7. So let's call it a night or an evening.
Thanks a lot to everybody who participated.
Thank you indeed.
That was really fun discussion.
Thanks.